questions for equilibrium. We're going to go through a few different types of questions involved with equilibrium and do some calculations and try and work out how to find the number of products and reactants we have in a certain system that is at equilibrium. We're also going to look at how we can use the equilibrium constant to find out if something is in equilibrium and what will happen if it's not. So the first question involves that. So let's get stuck straight into it. We've got a few questions. I've got 1, 2, 3, 4 questions here, I think. So we're going to go through the first one, and I'll probably break this up into 2 videos. So we'll do the first 2 for this video and the second 2 for the other video. Now the first one is just using the equilibrium constant to see if something's in equilibrium or if it's not in equilibrium. So we've got a system where we have hydrogen and iodine reacting together to form hydrogen iodide. And this one says the equilibrium constant for this is 60 at a certain temperature, because you know if you change the temperature you're going to change the equilibrium constant. So the most important thing is this is at this temperature, and it's going to be staying at this temperature for the whole of the question. So we're not changing the temperature, so therefore we're not going to change the equilibrium constant. We've got 3 sets of conditions given here with 3 sets of ideas of like certain concentrations of different compounds and seeing if these are in equilibrium or not. So, and decide if the reaction is at equilibrium or will it form additional products. So if it's not in equilibrium and there's not enough product there, or if it will form additional reactants. So if there's too many products, and it will have a reverse reaction happening. So the first thing we need to do is write our equilibrium constant for our equation. And you know that the equilibrium K equals products over reactants. So it's the concentration of products over the concentration of reactants. So in this case, we're going to have our K as being equal to the concentration of the hydrogen iodide to the power of 2, because we have our coefficient is 2. And this is going to be divided by the concentration of our hydrogen and concentration of our iodine. So we have concentration of hydrogen iodide squared divided by concentration of hydrogen times concentration of iodine. And the units for that is going to be molar squared divided by molar squared, so we're not going to have any units for that at all actually. So that's an interesting thing there. If you don't understand the units, go back and listen to the podcast. And there's a link to that in the description underneath this video. So first of all, we have a first scenario, and we have the fact that all our concentrations are equal. So the concentration of hydrogen, iodine and hydrogen iodide is all equal to each other. And what we want to know if this is an equilibrium. So they're all the same and we're not too sure if it's constant or not. So K1 equals concentration of hydrogen iodide squared, which is 0.01 squared, divided by the concentration of hydrogen, which is 0.01 because it's all equal, times 0.01 for the concentration of iodine. Okay, I look at this and go, what is going to be? 0.01 squared to the power of 2 equals 0.0001 divided by 0.0001, and our K for this comes out at 1. Okay, now we're given that the K is 60, so this is not equal to 60. What it is, in fact, is a lot less than 60, so it's not in equilibrium. Okay, and how is it going to form equilibrium? Well, it wants to become bigger, so it wants more product, so it will form more product. So our first scenario there is not in equilibrium. Okay, and it will go for our Ford reaction because the K was smaller than the literature value, so therefore the K will the reaction will proceed forward and make more products. Our second one here, we have our same K, same equation for K, so we'll just substitute these values in. Concentration of hydrogen iodide was 0.3, so we've got 0.3 squared. So this is for K2, or KB for the B scenario, and divided by concentration of hydrogen, which is 0.1, times the concentration of iodine, which is 0.15. We'll look at what this comes out to. So what is 0 0.3, is it? 0.3 squared to the power of 2 equals 0.09 divided by what 0.01 times 0.15 is 0.015. Where are we? Just going to get the amount of decimal points right. Don't want to stuff it up here. Is 0015. I thought so. Yeah. Do this calculation, and we have 0.9 divided by our answer equals 60. So this equals the literature value, so this is in equilibrium. Because our K value came out as 60, it's equal to what it tells us, so therefore it's in equilibrium. Pretty simple like that. Our next equation here says our concentration of hydrogen and our concentration of hydrogen iodide is equal to each other, and they are 0.1. So we'll do K equals K3 equals concentration of 0.1 squared divided by concentration of 0.1, which is our hydrogen, multiplied by 0.001, and that equals to 0.01 divided by 0.0001. Now this equals, what does this equal? Where are we? 0.01 divided by 0.0001 equals, it's not 0, hang on, 0.001 divided by 0.0001 equals 10. Now this is not equal to 60 again. It is less than 60, so therefore it's not in equilibrium. The reaction will want to have more products form to make it larger, so therefore it will proceed forwards as well. So that's how we can use our equilibrium constant to work out if a certain system is in equilibrium or if it's not in equilibrium. It's a pretty simple question like that, and if you get some of those on your exams or your tests, you'll be pretty happy because it's as I said, it's very simple. Now we're going to move on to the next question, which is a little bit more difficult. Let's have a look at it. The next one is looking at how much will be there at equilibrium. We're given a certain situation where we're adding our reactants together, and we say at equilibrium the concentration of something is this. What's the rest of it? We have to think about what it's going to be. So let's have a look at this. A mixture of 0.75 moles of nitrogen and 1.2 moles of hydrogen are placed in a 3-litre container. Straight away we can get concentrations, because we've got moles and we've got litres, so we can work out concentrations, which is what equilibrium is about. It's about concentration. And when this reaction occurs, so it's just the ammonia forming reaction, reaches equilibrium, we have this much of hydrogen left over. What is the values of everything else? And what I might do is I might calculate the equilibrium constant for this as well. So, and what is K? What's the equilibrium constant for this reaction? So the way we work out this is when we want to find out how much is left over at equilibrium, we kind of put it up in a matrix style. Just follow what I'm doing here. I set up the initial, how much we started with. I put down a change, and then I put down how much we have at equilibrium. Okay, and then I put the reaction above it. Alright, so I'll put the reaction here. Obviously do my equilibrium sign properly because I'm on a computer, so I can do that. Anyway, we look at how much we start off with. And this is all in concentration, so we need to convert these into concentration. So concentration of nitrogen is 0.75 over 3, because C equals N over V. And that equals 0.25 molar. So 0.25 molar is our concentration at the start for nitrogen, how much nitrogen is added into the system. Look at the concentration for hydrogen. It's 1.2 moles in 3-litre container. So 1.2 divided by 3 equals 0.4 molar. So that's 0.4 molar. And then at the start, we don't have any ammonia at all, so it's going to be 0 for ammonia. What we want to look at is try and fill in how much has changed and what the concentrations will be at equilibrium. Now, it tells us that we have hydrogen as 0.1 molar. So this is at equilibrium. We've got 0.1 mole of hydrogen. So 0.1 mole of hydrogen there. At equilibrium, this much molar. So that means we have a change of 0.3 moles. 3.3 molarity, whatever you want to call it. Concentration is going down by 0.3. Now, this means that this change thing here is in the ratio of our stoic ratio, our coefficients. So if we lost 0.3 moles of hydrogen, we're going to lose 0.1 mole of nitrogen. Because for every 1 mole of nitrogen that reacts, we get 3 moles of hydrogen. So therefore, it's going to go down by 0.1. So it's going to be left with 0.15 molar. And therefore, what does that change over this side? If this was 1, over here, it's going to be plus 0.2 molar. So we're going to have 0 plus that equals 0.2 molar. So we're seeing our initial, we're working out what our change is going to be, and then we're going to work out what our equilibrium concentrations are going to be. So obviously our concentration of ammonia at equilibrium equals 0.2 molar. Our concentration of nitrogen at equilibrium equals 0.15 molar. And our concentration of hydrogen at equilibrium equals 0.1 molar, as it was given to you before. So there you are. From this information, we can work out what the K value is, and it's going to be our equilibrium constant. Looking at this equation, products over reactants, concentration of ammonia squared over concentration of nitrogen times concentration of hydrogen to the power of 3, because it's our coefficient here, to the power of 3. Looking at this, what's our units going to be? Concentration squared over concentration to the power of 4. It's going to be molar negative 2. We put in our values here. We have 0.2 squared divided by 0.15 times 0.1 to the power of 3. We chuck that into a calculator and we go 0.2 to the power of 2 equals 0.04 divided by 0.1 to the power of 3 equals times 0.15 equals 0.00015 equals 0.04 divided by the last one we had equals about 266.6 molar to the power of 2. Now, this actually probably isn't the K value for this reaction, it's just an example, so but this is how you do it. So please don't take this as the actual literature value for this chemical equation, because I'm 90% sure it's not right. But that's how you do it. It's right for this example that was given to you. Now I'm going to pause this, I'm going to stop it, and we're going to start our next 2 questions on a new video, because this is up to 14 minutes already, and that's too long. Alright, so have a look at this, make sure you understand it, and we'll move on to the next one.